Assalamu alaikum. Welcome to the lecture 8 of Unit First. The switching phenomena is explained by the various models of thyristors. The first one among those models is diode model. The second one is a two transistor model, and the third one is dynamic or transient model. The first one, diode model. In this model, the forward anode to cathode voltage is applied between outer P and the outer N terminals. That results in the forward biasing of this junction J1 and the forward biasing of the junction J3 and the junction J2 is reverse biased. That means the whole forward anode to cathode voltage is across this reverse bias junction J2. And we are also applying gate current between the terminals inner between the terminals gate and the cathode. This gate current is this gate current flows by applying the gate cathode voltage, that means Vg, between the terminals gate and the cathode. That means this junction J1 is represented by a diode of diode representing this junction J1. This will be diode representing the junction forward junction J3, and this junction J2, which is reverse bias, this is represented by this diode, just like this. And this here, this represents the gate terminal. One method of explaining this is since this is reverse biased junction J2, that means in across this junction this will be there will be negative stored charge carriers, and across this there will be positive charge carriers. Now if gate current is applied between gate and cathode terminals, this means due to this gate current, this inner P layer is flooded with number of positive holes. They may neutralize this negative stored charge across this junction, which results in reducing the thickness of this depletion layer. Greater the gate current, more will be the positive charge carriers that neutralize this stored negative stored charge here, and this results in the free movement of charge carriers across this depletion layer, or we can say this results in the removal of this depletion layer, such that across all the three junctions we have free movement of charge carriers, or we can say the SCR is turned on. The next method of explaining this diode model is when the gate current or when the gate voltage is applied between the gate cathode terminals, the electrons flow from this negative terminal to this positive terminal, or we can say the electrons enter into this into this outer end region. Since that means and there is no depletion layer across the junction J3, there is free movement of charge carriers. That means these high number of electrons passes through this junction G3, and this inner layer P2 gets flooded with with the high number of electrons, or we can say or we can say this inner layer is flooded with number of electrons. Flooded with large number of electrons, and this inner P layer loses its property as a P layer, as this layer is lightly doped, and electrons from N2 are these electrons now these electrons, being minority carriers in this P layer, easily crosses the junction J2 and gets accelerated with the energy E. That means the charge of an electron multiplied by the anode to cathode voltage, that is all across this junction J2. Since these electrons gets accelerated with this energy, they may strike the covalent bonds of silicon atoms and may generate electron hole pairs in this n1 layers. Again, holes being minority carriers, holes in this that means this again holes in this layer, because this is the n1 layer, and here the holes are minority carriers. They get these holes reach the junction P2, and this phenomena repeats thus, or we can say this junction J2 becomes flooded by crossing of the minority carriers on the both sides, and the conduction of this device takes place. Due to the movement of these charge carriers, this depletion layer vanishes, and free conduction of and free movement of charge carriers occurs across all the three junctions, or we can say the AR is in the on state. The another model to explain to explain the thyristor's operation is the two transistor model of the SCR. This figure A shows the diagram of this thyristor. The two transistor model is obtained by bisecting the inner two middle layers along the dotted lines, which results in the formation of two halves, as shown in the figure, with junction J1 and junction J2, one half, and the second one with the junction J2 and the J3. That means the three this transistor, this is the P1 N1 P2 transistor T1, and this is represented by N1 P2 N2 transistor. T1 and T2 are PNP, and this is the PNP and the NPN transistors, such that the collector current of T1 provides the base current for base drive for T2, and the gate current and the collector current of T1. T1 and T2 are PNP and NPN transistors, such that the collector current of T1 provides the base drive for T2. The gate current and the collector current of T1 provides the base current for T2. This is just like the previous circuit. We are applying the forward voltage. This is the load, and this is the gate control circuit. That means the gate voltage is applied between the gate and cathode terminals. Here only that means we have this whole SCR is divided into two transistors. This is the transistor T1 and this is the transistor T2, and this gate plus this collector current is basically it forms the base current or driving current for the transistor T2. This represents the anode current. This is the cathode current, and this is the gate current. Now, when a small gate current is applied to the base of T2, the applied collector current, which is also the base current of T1, generates a very large collector current of thyristor T1. This current is again supplied. This current is again supplied to the base of T2, and thus provides a positive a positive feedback is initiated, and within a few microseconds, saturation is reached. Thus, this current is only limited by this external load that is connected with the transistors, or you can say that is connected with this thyristor. By applying KCL to the previous figure C, this cathode current is basically the combination of two currents. One is the anode current and the gate current, and this anode current is itself made up of two currents, that is the collector current of transistor T1 and the collector current of transistor T2. Since we know that for each transistor, the collector current is related to the emitter current, as this is the collector current IC, that is equal to alpha times the emitter current, and here for the first transistor the emitter current is the anode current, and this is the common base current gain. or we can say this ICBO is the common base leakage current of collector base junction of transistor T1. That means this is the IC1 represents the collector current. IA is basically the relation is IC is equal to alpha times IE plus ICB naught. For this transistor T1, this will be equal to IC1 is equal to alpha 1. We represent this whole by subscript 1. IC1 is equal to alpha 1, that is the current gain, common base current gain. This is the IA, that is the emitter current, and this will be the ICB not 1, that is the leakage, common base leakage current. And for the transistor T2, this collector current IC2 will be equal to alpha 2 IK and plus ICB not 2. Putting the equation 2 in equation 1, and by rearranging the items, we get this IA is equal to alpha 2 IG plus ICB naught 1 plus ICB naught 2 divided by 1 minus alpha 1 plus alpha 2. Or by we can say by this equation, from this equation 3, if alpha 1 plus alpha 2, that means they approach towards unity, this IA 1 minus 1, that will be 0, and this IA will approach to the infinity. This may result in the turning on of SCR. That means for turning on of SCR, this alpha 1 and alpha 2 must approach to unity. If this alpha 1 and alpha 2 is less than 1, that means the device is not turned on, it's turned off, and this IA will be very small, and that will be equal to leakage current. That means ICB naught 1 plus ICB naught 2. If IG is equal to 0, that means alpha 2 into 0, that this whole term will be equal to 0, and this IA will be equal to ICB naught 1 plus ICB naught 2. That means this is equal to the sum of leakage current, sum of leakage current, or we can say the alpha IA anode current is very small. If somehow this alpha 1 and alpha 2 is approached to unity, this 1 minus 1 will be equal to 0. Anything divided by 0, that is equal to infinity. That means IA approaches to infinity, and this occurs only alpha 1 and alpha 2 approach to unity only when we are applying some gate current. This IA will be that means when we are applying gate current IG, some IG such that alpha 1 plus alpha 2 approach to unity, this IA will be infinite, and or we can say the SCR is turned on. Or we can say that on application of small gate current, that means if we are applying the small gate current, this gate current, basically this IB2 will be equal to IG, because of this base current, or we can say we are applying not only gate current, we are applying the base current for the thyristor T2. Basically, if we are applying the base current, emitter current increases, and this emitter current here is the I cathode. Since the emitter current and the emitter current increases, or we can say the alpha unity alpha 2 of this gain alpha 2 of this transistor increases. The increase of this alpha 2 results in the increase of the collector current IC2. As collector current is basically equal to the sum of emitter current plus base current. This collector current is basically the base current for the transistor T1, and transistor that emitter current for this transistor T1 will be that anode current, is anode current IA. Since the anode current increases, we can say the alpha 1 that this gain alpha 1 increases. If emitter current and base current increase, that means we are saying this collector current increases. If this collector current increases, we can say that the base current for this P2 base current, which is a combination of IC1 IC1 plus IG. As initially we have started with only gate current, that means this IC1 we have taken this, we are saying that this collector current C1 is 0. We have started with this base current IB2 is equal to IG. Now at this stage, uh, this base current further increases by adding up of this collector current IC1 plus IG, and this phenomena goes on increasing until and unless this alpha 1 and alpha 2 both approach to unity. Um, or we can say the increase of this by the increase of this loop gains alpha 1 and alpha 2, each each transistor drives another one into saturation, or we can say this device reaches into the conduction state and the anode current becomes very high or infinite. However, practically this is limited by this resistor, external resistor R only. The voltage across the device is approximately same as that of a PN, is same as that of a simple PN junction. This is diagram showing that alpha builds up rapidly as the emitter current is increased, and the highest value of it is unity. Now, the third model to explain this thyristor switching is the dynamic or transistor transient model. This is the simple PNPN thyristor. That means this whole it's divided in it's made up of three junctions J1, J2, and J3. These all the three junctions can be represented by and J3 is represented by resistance and capacitance connected in parallel. That means this junction J1 is represented by RJ1 in parallel with the capacitance CJ1. Junction J2 can be represented by RJ2 in parallel with capacitance CJ2, and RJ3 and the junction J3 by is represented by RJ3 in parallel with the capacitance CJ3. The junction capacitance, since we are applying the forward voltage, that means the junction capacitance CJ1 and the junction capacitance CJ3, it becomes insignificant as it is short circuited by this resistance RJ1 and RJ3. That means RJ1 is equal to 0 because as we are defining that it is forward biased. RJ3 will be equal to 0 as it's forward bias. And the only and the resistance across this because of the reverse bias, the resistance across this junction becomes infinite, which may cause the junction capacitance of this layer, this junction as infinite, or we can say the charging current, or we can say the charging current here is equal to I junction J2, the charging current across, because this resistance is infinite, which causes this capacitance infinite, or we can see the charging current ICJ2, that will be equal to C dV by dt, because we know in case of capacitor the current will be equal to I is equal to C dV by dt. Here the C is CJ2 and the voltage here is the same voltage, that is same blocking voltage that is across this junction J2. That means this will be equal to V anode to cathode voltage. The charging current ICJ2 is equal to CJ2 multiplied by differentiation of V anode to cathode voltage divided by dt. If that means if a rapidly rising anode to cathode voltage is applied across the anode cathode terminals, the magnitude of IJ2 becomes very large. It reaches to the gate layer P2 and it behaves similar, this capacitance current ICJ2, as it's very large due to a sudden rise in anode to cathode voltage, this behaves like the gate current, and if this IJ2 is sufficiently larger than the latching current of is larger than the latching current of anode current, SCR comes into the conduction state without applying the gate current. That means this is also one method of turning. That means if the rate of rise of anode to cathode voltage is very high, this may result in the increase in the capacitance junction current. This capacitance junction current behaves like the gate current, and it may this may result in the increase of the anode current. And once this anode current reaches that latching part, the SCR will remain in the on state even if no gate current is applied. By explaining all that turning on turning off periods, or explaining all the three models, we came to know that the only method to turn off the SCR is by applying the reverse voltage. And this reverse up voltage is also applied for some finite period of time. That means gate current has no control once the SCR is turned on. Or we can say the IA should be reduced below the holding current, only in order to make this alpha 1 plus alpha 2 is equal to 0, so that this internal regenerative action turns off. IA drops to 0. After IA drops to 0, the device should be reverse biased for a duration, that is TQ should be greater than T off, where T off is known as the device turn off time and TQ is known as the circuit turn off time, as explained earlier in the switching in the turn off switching method.